Okay, when I go over these with you guys, and I apologize for something because of the recording for the at-home learners, so I could flip between video of me, which might be necessary at some points today, and the screen. It puts this in the bottom right-hand corner, and I can't get rid of it if I want to flip. So if that's in the way, I'll scroll enough so you can see as we go, okay? So anyways, just to get the hang of like what we, when I give the answers for this, we'll discuss all of them very quickly. But if there's anything, even after I quickly discuss it, if it still doesn't make sense, make sure you say something. I'll go into it or spend a little more time on it. You could choose to check your own, because we could have a test or a quiz eventually, and this will be one of your primary things to study off of for it. It's up to you if you want to physically erase on Squid your file and change it, but this is going to be posted anyway after we go later in the day after we go over it. So the exact key is here. That way you can pay more attention instead of scurrying and crossing stuff out. This is going to be posted right on the same assignment where it all came from, and it'll stay there for the year. You can go back to it any time. But I would probably download it so you have it in your folder so you don't have to go through back whenever we do have a test or a quiz and find them all again. Does that make sense to everybody? Okay. All right. Anyways, a couple quick things before we get into the exact questions on here. The main things we're focused on is knowing what a vector is as opposed to a scalar. So real quick, what's the main way a vector is different from any scalar quantity? One big thing. Right, vector has magnitude and direction. Scalars are just magnitude. Magnitude's a fancy word for? Yes, size, or the number once we have real values, right? So if you remember that, that's a start. Then we discussed a lot of just different, like the moving man guy on the screen. We're going to come back to that for a different reason today. To go a little further into speed and velocity, but you can't understand speed and velocity until you understand distance and displacement, because it goes right into making those similar or possibly different. So anyways, we'll review the distance displacement stuff through these questions. All right, the first thing you had to do, and some of these I didn't mention yesterday. I didn't bring up acceleration at all yesterday, right? Like the main points I will, but sometimes there's going to be those questions where you, just from paying attention, you won't get. You'll have to go in and look them up where it was provided in the lesson. So anyways, out of the 5 things listed, all 5 of these things happen throughout this lesson. Some of them we just didn't get to yet. The ones that are scalars, that don't care about direction, are distance and speed. Okay? And the ones that are vectors, they give magnitude and direction, are displacement, velocity, and acceleration. So we kind of already answered this right at the beginning of class. So number 2, A, scalar quantity. Number 3, B, vector quantity. All right, then the next part tells us a little bit, kind of defines distance and direction for us again within there. We get some true and false questions. True or false, an object can be moving for 10 seconds and still have 0 displacement. We got to focus on what word they use. They use the term displacement, which is a vector. So the answer is true because of an example. Now, when it says explain, obviously you don't have to be word for word. If what you said means essentially what was here, you could probably write it a lot. They get a little wordy in the answer key, okay, than what's probably necessary. So as long as you pretty much meant what's there, you don't have to change it to that whole thing if you're changing stuff, okay? But the main thing is this one's true. And we showed some examples of this yesterday. So how can something actually move for 10 seconds, or any amount of time for that matter, and still end up having a displacement of 0? Yes? Right. If it ends up back to wherever it started from, that's how we define displacement, from where we started to where we ended. So you could move for 2 hours. If you come back to the same spot, you have 0 displacement. And remember, although displacement is a vector, if the magnitude of displacement is 0, that's the only time it's allowed to not have a direction attached, because it wouldn't make sense. You came back to where you started, you didn't displace right or left or up or down from where you started. So any non-zero magnitudes of displacement need to have some significance of direction on them. Okay? All right. Another question with the same idea. Suppose that you went along 3 different paths from location A to B. Notice A to B is set up the exact same way in all three, right? They don't change like where those are, the positions of A and B. That's the first thing to consider. Which path would your distance be different from your displacement? And as you can see, the right answers are 1 and 3. Distance doesn't care about turns, right? It's a scalar. So even though this one turned, it doesn't care. It imagines as if it were all just a total. So what's the shortest distance between any 2 points, guys? Yeah, straight line, right? So because of that, this one has a different distance than this one, right? And this one has a different distance as well, because it totals up the paths. But so that's what we're looking here. Which would be your distance traveled be different than your displacement. Paths 1 and 3, the one where there were turns. All right? Because displacement is from where I started to where I ended. They all three have the same displacement, don't they? They all started at point A and all went to point B. All right? But as far as how the question asked this one, we leave out path 2 because path 2 would have the same distance as displacement. We gave examples of this yesterday. If you travel wherever and never change direction once, and you travel to somewhere, that is when distance and displacement can be practically the same, at least the same magnitude. Okay, technically, the one still needs to have direction tacked on if we're writing it down. But magnitude of distance and displacement is the same in path 2 because it never changed direction, straight line. Make sense to everybody? Okay. As long as we have the idea down, you're good. Now we're going to use that idea in the second page to throw in some numbers. So this would be like what we were doing yesterday, throwing in some numbers on the guy on the screen. All right, so we can see that your house is 3 miles away from your friend's house. They are using east and west. I mentioned something yesterday because of this. If it doesn't mention a direction presented to you in the situation, you can choose what you want. But obviously, by them putting that there, it wants you to use east-west, right? So do that. Don't use right-left if somehow the question or problem presents the directions that it wants you to use in some way like that. So it says that we go to a friend's house, then you walk home. So what's the distance? 6 miles. You total up. It doesn't care that you turned around to calculate it. You just total up every piece of the trip. Displacement, 0, because we came back to where we started. Pretty easy, right? All right. Kind of a two-dimensional walk on this one, on this grid, where it does tell us that each square is 1 kilometer along its edge. The person walked a distance of total, we have to count it all up. If you count every edge of the box around, it's a total of 31 kilometers. Okay, if you did that right. And it gave us a bunch of choices here. This person has a displacement. This one's super easy too, as long as you realize here's where we started, here's where we ended, right? We started 3 spaces to the right. But notice here in the corner, they're telling us to use north, south, east, west, right? By putting that there. They're implying that. So we should actually say 3 kilometers east. And that leaves C as the only logical choice there. We good so far? And just one where it turns around a little bit. It gives you some rules here. I'm not going to read it all. Obviously, if you did it, you read it. But this skier makes some changes in its motion along these points. What doesn't matter right now, but will later today when we get on to the new part, it gave you some times, how long, right? Plain old questions on distance and displacement, time has nothing to do with. But you're going to see a very similar situation coming up in your next study guide where it asks you something where time matters, okay? So those times really don't matter other than them just being intervals you walked in from the points described. So in part A, what distance was traveled by the skier during the entire 3-minute walk? And following the directions up here, it said distance, we total it all regardless of changes in direction, and you should have got 360. Here in the key, it breaks down each segment that was described below that we would add together to get that. Are there any questions on that? And I'll go through it in more detail if we need to, so don't be afraid to raise your hand. We good? Okay, part B, what's the net displacement of the skier during the entire 3 minutes? So when we start at point A and get to point D is the entire 3 minutes. And we don't care what it did in between. From where we started to where we ended, that's 0 to 120, we ended up to the east of them. What's the displacement for just the second minute? Just the second minute would have been from 1 to 2 minutes, and that would have been starting here, ending here, 120 meters west. And finally, what is the displacement during the third minute from 2 to 3? That would be from here to here. We're on the 40 position mark to the 120. That would be 80 apart, 80 east, because in the later point D at 3 minutes, right there. All right. The minute stuff wasn't necessary to do the calculation other than knowing that's when you were at those points. We okay with all that, guys? All right, so I will post this by the end of the day, or hopefully at the end of the period, but no later than the end of the day, and it'll be available. And now we're going to go on to discussing some stuff about speed and velocity. All right, well, what we already saw, we answered earlier, and we probably just know from hearing those terms, they're similar, but they differ in a way that like distance and displacement differ. One's a scalar, one's a vector. So which one was a scalar? Speed or velocity? Harris? Speed, leaving velocity as a vector. Just like distance displacement, in the right circumstance, they might have the same magnitude. But in another circumstance, they might have totally different magnitudes. It's all about did they change direction or not, just like distance and displacement. As a matter of fact, distance and displacement are used when calculating them. We're going to get our first super simple equation of the year. And it's one you're probably already familiar with, but we have to be careful how we use it. Okay? It's actually on the new study guide. So if you don't have the new study guide opened up in today's post, that's the old one. Hold on. I'm going to put the new one. This is the new one. All right. There's some formulas on the second page, so you don't have to write them down. The two small formulas are already there. We'll get to that in a second. But set up similar to the other study guide you did last night. The first page is like the concepts more than some calculations and tiny bit of mathy stuff. All right. Anyways, let me ask you some general questions first. If I took any one of you and you guys, we just told you to walk or run from this wall to this wall, from end to end in the room. And we wanted, whoever that person was, we wanted to figure out how fast they were going. What kind of tools or device could accomplish that? Give me one. Good. A speedometer on board, right? You're right, but most of us don't have an onboard speedometer when we're walking, right? Vehicles do. But you're right, that's one device that could possibly do it. Give me another way we could figure it out. Yeah. A stopwatch with what else? A stopwatch alone won't. You're getting there, though. Right, some kind of measuring device. All right, that's the answer I'm really looking for as far as the calculation here. Okay, because neither one of those, the measuring device, the meter stick or whatever, probably a longer one we'd use for. Here's my calculators from wall to wall, but whatever. Some kind of tape measure, meter stick, something like that. That alone won't give me how fast. A stopwatch on your phone, whatever. That alone won't give you. What would you do with the values you could get off of those to figure out how fast you were from there to there? Or from wall to wall? Yeah, good. Divide them. It's a simple little formula. So probably refer to it just V equals D over T. How many heard of that formula before? All right. If you didn't, it's a simple rate equation. Anything time we divide something by time, we usually refer to it as a rate equation. The rate at which we went from here to here. And it's pretty simple. There's another option, though. Sometimes some people say, and we'll discuss a little bit more later about. So, yeah, we could have a stopwatch and some kind of measuring device. Absolutely. That's the one we're going to focus on. We could have an onboard speedometer. What's another way? Now, while you're thinking about it, an onboard speedometer, just to get a little bit how they work, like I said, it wouldn't be typical to have one on a person, but on a vehicle, later in the year we get to rotation. And we'll learn some differences between linear motion, straight line motion, and rotation of a wheel. Actually, a speedometer on a wheel measures the rotational speed of the wheel. in a unit you're not familiar with, probably. And either mechanically or digitally, by the time it gets to your speedometer that you could see, whether it's digital or a needle, it converts it into a common linear velocity like miles per hour. Yes? Yes, it would, but that's for another time, but you're absolutely right. We'll bring that up. We're going to learn an equation that it's basically you have to know or like mechanically calibrated to follow in order to do that. Because it is true, if you drastically change the size of your wheels and don't get it recalibrated, your speedometer will not be right. So that's the technical reasons why come later in the year when we get the torque and rotation and stuff like that. Okay? But anyways, that's just a quick version of how a speedometer does it. Okay? But there's still one thing. Hopefully you never got caught by it. Go ahead. A radar gun, right? Sometimes I like to sit out by the parking lot in the morning and just hold a hairdryer out my window and just watch people slow down. It scares them. It's fun. Anyways, how they work, again, isn't really relevant to, like how they work isn't relevant to what we're doing now, but it's relevant that it's a way to take a speed. But I'll give you a quick version of this. This is something when late in the year, one of the last topics we get to are waves. And what they do is shoot out an invisible wave, electromagnetic wave, that travels at 300 million meters per second, the speed of light. And that's why when you cop hit us with a radar gun, just like that, it gets the reading. Because that wave is traveling so fast, it bounces off your car and goes back to this gun in such a small amount of time you can't imagine. And then how it reads your speed is something called the Doppler shift of waves, and we will learn about that. All right? When waves bounce off a moving object, it affects their frequency. And so the original wave has a certain frequency. The bounced wave changes because it hits something's moving. It either gets a little bit higher in frequency and a little bit lower. And there's a mathematical correlation to how much the frequencies change compared to how, the speed of the thing it bounced off of. And that's programmed into the radar gun. A guy named Doppler with that last name figured it out. That's why it's called the Doppler shift in general. Other waves do it as well. Yeah, question?
If you're like running and someone's going by you at 45 miles per hour and you're like running 5 miles per hour, will it read 40?
Okay, good question. Let me just answer it briefly. That's getting into the kind of question that deals with a concept called relative velocity, which we do cover at some point too. So we'll get into more detail of that question later. But to answer it simply, you're basically saying, an equivalent question would be, what if the cop was moving and you were moving? A few years ago, I would say it wouldn't read it correctly, okay? Because the technology not too far back couldn't do that, and not all of them still can. But from what I've read and looked at about this, especially in the last couple of years, there are ones that they do make. How many of that are actually out there in use, I don't know. There are ones they do make that it's wired into the speedometer of the vehicle, and it has to know what it's going at to be able to calculate that, and it can happen. But most ones that are just handheld ones that they just hold out there when they're stopped wouldn't be able to have that capability.
So if you were going the opposite way, you would just add your speed?
And that's when we learn the Doppler shift question or equation late in the year, you'll exactly see how that math works out. Okay, because the Doppler shift could work with the source stationary and the detector, what it's bouncing off, we call it a detector. It could work in different combinations, basically. So, like I said, just throwing this out there now, the main reason I bring up radar detector, though, for now, is just that that's a way to get speed. Now, of all three of those cases, the third page I told you don't worry about had something to do with instantaneous speed and velocity, okay? Instantaneous means at the given instant, right? So, we got to understand which one of those methods we named are instantaneous and which one are not. And if they're not, then we need to call it something else. Okay, we'll get to that. So since we're on the radar gun right now, the radar gun, because it happens so quickly, because of those waves bouncing, I mean, it's fractions of a second that it really takes because of the fact of how fast they're traveling. Because it reads it so quickly, we could take that as an instantaneous velocity. It holds up in court that if you get a speeding ticket as an instantaneous velocity when they pull that trigger and get you on it. Okay? When you use a speedometer, it's in real time running off the rotation of your tire at that given moment. So you could trust that your speedometer, unless there's a issue with it, is reading instantaneous velocity. But when we use one of these and one of these, I should have said instantaneous speed for the speedometer, by the way. I think I said velocity. We'll get to the differences in a second. But when I use a measuring device, I don't know why I held this up. This is a laser pointer. That has nothing to do. I meant to say a stopwatch. When I use one of these, or any kind of measuring device, and a stopwatch to figure out how fast somebody's going, does that give me the speed at any given moment of their travel? Yes or no? In other words, what I'm asking, let me get it up on the screen here. Let's take this guy again. If I say right here, we have our measuring device right here, right? If I time how long it goes to go from there to there, I had to pause it real quick so it's not super accurate, but there's my stopwatch, right? And what did somebody tell me I do with those numbers? He went 10 meters and it took 0.9 seconds. What would I do mathematically with those numbers to figure out his exact speed as a value? Yeah. Divide them. It would be the distance divided by the time. 10 divided by 0.9. Whatever comes out to be. However, my question is that an instantaneous velocity when we divide those? It's an average. Very good. Because when we do it in that fashion, when we time from point A to point B, this guy could have traveled, let me reset it. This guy could have went real fast for the first 2 meters, really slow for a while, really fast again, really slow for a while, really slow, really fast again at the end, right? So, if I now take that chip, the first one was more steady looking than I did, right? But this one, it was all over the place how fast he was going. He still ended up at 10 meters. We still have a time. It's different because he used different rates in between. But when I take 10 divided by 5.1, and I get close to 2, right? We'll just approximate to 2 for the time being. We get to close to 2 meters per second, right? But that is doing it that way is his average velocity. Because he obviously didn't travel that the whole entire time, right? So when using the equation V equals d over t, at best, it's the average velocity or speed of the person. We'll get to those technical differences in a second. V equals d over t only finds that as an average unless we know some more information or we're present to see it. The only time using that formula gives us an instantaneous velocity if he was traveling how the whole time? Yes. The same, or in other words, constant, right? Everybody agree? If we were there to witness it and saw this person traveled at the same speed from point A to B, and we had these numbers and run them, it's better than average because we were there to see it. He didn't slow down, stop up. But obviously, a lot of stuff we're going to do this year is on paper and given to you. And you weren't really physically present to see it happen. So you can't ever assume something was moving constant unless you were told they were. So if I just simply say, without showing you up here, this guy moved from 0 to 10 meters in 5 seconds, you calculated that, and best, one more time, is what kind of value? Average, right? At best. It could be instantaneous at any given moment, if we know for sure some way, shape, or form he was going constant. Does that concept make sense to everybody? All right? Now, in this course, we do not mathematically do anything with instantaneous velocities. Our math only really is for average ones. The only instantaneous ones we deal with is if it's that situation where it was constant. Okay? Here's the reason why. You need calculus to handle instantaneous rates that change from point A to point B. It's actually one of the main reasons Newton started developing calculus. When we get to graphing, we'll give you a better insight to why. When you see the motion graphs, this equation, V equals d over t, Newton didn't wake up one morning and have an epiphany and say, oh my gosh, V equals d over t. He did simple experiments with motion. He plotted points. realized in the right experiments his graphs were linear. When they were linear, he applied, guess what's formula you should know? What did you guys call it in algebra? Slope-intercept form. What's slope-intercept form? Yell it out. Y equals mx plus b. But y's and x's are now real things that he plotted, not called y's and x's. And then he formed the equation that we are going to use right today and tomorrow. Okay? These equations do not come out of thin air. They either come from experiments or plugging in and subbing into other equations that came from experiments and coming up with new ones. We like mathematical substitution. None of this is made up. These are all discovery of just how the world happens to work around us. All right. So saying all that, that gives you a good background in that. Let me flip to the two equations on page 2. So now we know speed's a scalar, velocity is a vector. There's a slight difference if we do have measuring devices and a stopwatch or information just straight up given to me to be able to run these numbers and divide them. There's a very small difference between the two formulas in words, but we now know it could be a huge difference because if we remember the difference between distance and displacement, right? So, if somebody asks you to calculate the average speed somebody is traveling from point A to point B, since speed is a scalar, we would use distance to calculate it because distance is a scalar. Make sense? All right? Since velocity is a vector, we would use displacement to calculate it since displacement is the corresponding vector if it goes over it. Can these two magnitudes be the same? Yes, if the guy never did what from point A to point B? Change direction. Just how we defined yesterday with distance and displacement. Can the magnitude of distance and displacement be the same? Yes, only if they didn't change direction. So when you do calculations, and they asked you for both of them, if the guy never turned around, the person, the object, whatever, if they never turned around, then your numerical magnitude answer for both of these will be exactly identical. But technically, since this one's a vector, you still need to include what on the magnitude? Yeah, good. A direction, right? Go with direction that's presented. If not, make up your own and be consistent, all right? So with that in mind, you're going to use those two little formulas. I mean, they'll just be division a little bit today. I do not want you to go on and do the 4th page for homework. We're going to go over tomorrow the first 2 that you're going to start now and finish for homework, okay? And once we have that concept down, we answer those questions, we'll go on to some basic problems, 11 through 14 on page 4. I mean, if you really want to start them, you can, but I'm not assigning those right now. For tomorrow, I just want the first 2. I don't think I noted that on the assignment itself for today, so that might not be worded anywhere on Google Classroom, but all I want you to do is turn in the first 2 pages. And you could turn in the whole thing and just have the first 2 pages complete. That's fine. And like anything, if you need to, go back to the tutorial and to the link that's provided and read a little bit more about it if something doesn't make sense. And just FYI, these calculations are so simple. Those are elementary formulas. Really simple. Normally, if anything's even kind of difficult, we do pull-out example problems of. I think this is pretty much straightforward enough that you didn't need to see a full example through what we just explained. Okay? All right, so use the remainder of the time to start this. If you don't get done, the rest is homework.